Okay, this is the logistic model. It's a differential equation that models population growth. And it's a very realistic, as far as textbook math goes, it's a very realistic model for population growth because it factors in something called carrying capacity. And if you, depending on which science classes you've taken, carrying capacity is the maximum number of organisms of a particular population that an environment can support. Things that limit your carrying capacity are things like food. You can grow until you run out of food, and then your population starts to decline. Or disease, natural predators, the amount of space you have, humans, obviously no magic, but that's a given. Um, and those are all things that can limit the carrying capacity. And that is factored into the logistic model, which makes it a very realistic model. The general formula for your logistic differential equation is this thing right here. dp dt is kp 1 minus p over c. P is the actual population. And one thing I kind of wish I'd changed on here, your solution is the solution to the differential equation is some function p in terms of t. I'm going to call it p of t equals c over 1 plus ae to the negative kt. And c is the carrying capacity. That is the maximum number of organisms that the environment can support. And ideally, the population will grow until it gets to the carrying capacity, and then it will sit at carrying capacity forever. In perfect harmony with its environment. Now, obviously, that's not realistic. Something will happen to knock it off the carrying capacity. But in textbook math, as time goes on for forever, the population does approach that carrying capacity. And once it reaches carrying capacity, it just sits there. In utopia, wonderful. Okay, here's an example of a logistic model problem. I'm just going to do one. The State Game Commission um, releases 40 gnomes into the game refuge. After 5 years, the gnome population is at 104. Now, they just gave you two pieces of information that can come in handy. They initially released 40 gnomes into the refuge thing, so that means my population at time 0 is 40. That's a given information. And then they tell you that after 5 years, the population is 104. So then we know that P of 5 is 104. That's probably going to come in handy. The commission has determined that the rate of growth of the gnome population follows this differential equation. And when I see this differential equation, I recognize this as logistic. And you need to get to where you recognize that also. Now, if they're very nice, they will say follows the logistic differential equation, yada, yada, yada. But that is not always going to be given to you. So you need to recognize the logistic differential equation. And they do tell you that t is measured in years. First thing it wants you to do is find the model P of t that gives the population of gnomes after t years. And that's really the hard part. B and C are going to be very easy. But for part A, I know the general solution is the carrying capacity over 1 plus AE to the negative KT. And we can tell that the carrying capacity is going to be 4,000. That's in the problem. It's P over C. So there's my carrying capacity. So I'll go ahead and take out the C and put in 4,000. And then we will use this information, P of 0 and P of 5, to solve for A and K. I'm going to start with 0. P of 0 is going to equal 4,000 over 1 plus A e to the 0, which is nice because e to the 0, k times 0, is just going to be 1. And I know that my population initially was 40. E to the 0 is 1, so I'm going to get rid of the e to the 0 because that just equals 1. I'll put a little thought bubble around that. And then we solve this equation. Now, we are all fairly smart people, and I assume you can solve an equation. I will start by multiplying both sides of the equation by 1 plus a, and then I'm going to do some magic, and we will get 3,960 divided by 40 is going to end up giving you your value of a, and we will just throw that in a calculator to get the final number, although I'm sure it's going to be quite sexy. And we do get something sexy. We get just 99 for A. Now, if you know me personally, you know that I absolutely suck at memorizing formulas, and I'm actually quite impressed that I was able to go straight to my logistic solution there. But if you do have the initial population, your constant A can be found with this formula. It's your carrying capacity over P of 0 minus 1. And I just worked that out real quick while I had the video recording paused and I was finding the solution there. So now that I know what A is, I can go back to my equation and I know that P of T is going to be my carrying capacity, 4,000, over 1 plus 99. Where'd I go? E to the negative kt. Okay, now I need to solve for k, and this one's not going to be quite as nice, and I don't have enough room here. I didn't plan this out very well. But in order for me to solve for k, I'm going to need to go with my second piece of information up there. So if I pull p of 5 equaling 104, let's see, p of 5 equals 104, and I'll plug in 5 for my t, so 4,000 over 1 plus 99 e to the negative k times 5, I'll just say 5k, is equal to 104. And then we will solve that equation. And these are calculator type problems. Obviously, you're not going to be able to solve for k and get any reasonable answer without a calculator to give you a nice decimal to work with. So let's punch this in the calculator and get an answer. All right, and you end up getting for k, I had to shrink this up to give me some room, k being where'd it go? 0.194? Ah, geez, what happened? Yeah, 0.194. Now, remember that we're going to use this answer later on, so we do need to store this in our calculator. I'll just store that for a. Actually, I'm going to store it for k, because that makes sense, because it is k. Now that I have k and I solved for a, we roll that into the actual solution, and my final equation is P of T equals 4,000 over 1 plus 99 e to the negative 0.194, whoops, forgot the decimal, T. And I actually, since I have my calculator, I'm going to store that in my calculator for y1 of x. I'm going to do that right now, and then we'll use it to answer B and C. All right, so I have that now stored in my calculator. And part B, all right, it says use the model to estimate the known population after 15 years. That's real simple. We'll just plug 15 into the equation, and I punch that in the calculator, and you get 628.538. Now, normally in AP Calculus, we round to the third decimal. However, we are talking about living creatures, and gnomes, you may not know their reproductive habits, but they reproduce kind of like humans. They never have part of a gnome. You either have one or you don't. So we will say that at this point in time, there are 628 gnomes. We haven't quite made that 629th one yet. So there we go. There's the answer to part B. And part C, find the limit as t approaches infinity. The answer to part C, that is actually a carrying capacity question. What happens to the population as time goes on forever and ever and ever and ever and ever? And that's going to be the carrying capacity. So as time goes on towards infinity, the population is going to level off at 4,000. Now, it may not actually get there. If you were to actually look at this on a calculator using these numbers, you would end up with like 3,999 and a bunch of decimals after that, 0.9999999 stuff. But it does approach that carrying capacity as time goes on towards infinity. So there is one logistic model. They're pretty nice, pretty straightforward. You just have to be able to recognize the logistic differential equation and know what the solution is. Because if you don't know the solution, the process of actually separating and solving this is a complete pain in the butt. So please take your time to memorize and learn this solution to the differential equation. So there you go.